Okay, I guess I'll get started. So the first set of worksheets for chapters 21 through 24 are due on the 23rd. They're up on Brightspace as quizzes. And so you can get started on those for the early chapters. Homework number 1, consisting of problems from the book, is also due on the 23rd. It's also posted on Brightspace. So, and then lastly, make sure to sign in on the sign-in sheet so I can correctly mark you for attendance. Doesn't affect your grade, but it will be recorded as you were missing class. Any questions about any of that? Our first test will also be on the 23rd. It'll be multiple choice. It'll be 60 to 70 questions. I haven't finished writing it up yet, so. And of course. So we're going to get back and continue on with chapter 23, which is light, telescopes, and the sun. So we'll look at we went over these last time, but we'll look at the wave properties of light as opposed to the particle properties of light. We'll talk about the types of spectra. We'll go over the properties that make telescopes with large mirrors more useful than those with small mirrors. We'll look at the advantages of radio wave and orbiting observatories. We'll look at the structure of the sun, and we'll look at the types of solar storms that occur on the sun. So we observe the world, the universe, primarily through electromagnetic radiation. That is light. Electromagnetic radiation is everywhere. It's not something you need to be worried about unless it is, of a particular type. If it is ionizing radiation, you may hear the term ionizing radiation. That's the type of radiation that is dangerous because it is radiation that when it comes out, it has enough energy to knock electrons off of atoms, which can disrupt DNA and cause cancer. So that's why gamma rays and X-rays, which are the highest energy electromagnetic radiation, and also ultraviolet light, can give you cancer. That's because they have enough energy to actually damage molecules, including DNA, and damaged DNA can mutate and can cause cancer. But things like visible light, infrared light, or radio waves, none of those are something you need to worry about in that context. They're not going to cause, the packets of energy that they release don't have enough energy to cause damage molecules and cause issues there. Now, it's perfectly possible to concentrate them enough that they could hurt you, but they're not like a radiation risk. They're somebody blinded me with a laser, or generally they're going to burn you in a nice, relatively straightforward, simple way. So electromagnetic radiation, it is all the same thing. It is all vibrating electric and magnetic fields. And the difference is just how fast they're vibrating and the wavelength they have as they travel. Because they all travel at the speed of light. So if they're vibrating faster, the waves have shorter wavelengths. So shorter wavelength stuff can act as larger lumps of energy. So these are things like gamma rays and X-rays. Then ultraviolet, we have the thin slice that is the visible light that our eyes can detect. Then we have infrared, which is near and far. And then we have radio waves, which includes the section for microwaves. So microwaves heat food because they excite a resonance in water or some other molecules. They make them jiggle, and that heats stuff up. But you don't have to worry about like microwaves or 5G giving you cancer. If you have a poorly if you have a damaged microwave that'll run with it open, you have to worry about maybe getting burned, but you don't have to worry about like weird, there's a lot of weird scare tactics out there. So one of the things is because it turns out when we deal with stuff that is really small, like light and like elementary particles, stuff has a tendency to both sometimes act like a wave and sometimes act like a particle. And light is one of the classic examples of it, because this is where it was first discovered that we could have stuff that sometimes act like a wave and sometimes act like a particle. So it has a number of properties that are analogous to waves. The wavelength of radiation can vary from several kilometers long radio waves to less than 1/1000th of a centimeter long. White light consists of a variety of wavelengths corresponding to the colors of a rainbow. Light bends when it enters another material in a manner that is due to its wave-like nature. Frequency is the number of waves that pass some point during a second. This is measured in hertz. Visible light varies from 430 trillion to 750 trillion hertz. But sometimes light will act like little particles or little lumps of energy. These are called photons. They're sort of analogous to bullets fired from a gun. They can exert a pressure called radiation pressure on matter. One of the two tails that comets can get is caused by material being pushed away by radiation pressure. There's actually a few satellites we currently keep stable by balancing them against radiation pressure. I think the Hubble might be doing that these days. Basically what happens is that as the stuff we normally use to align satellites starts to break, the people who run these things start to get more and more creative. And it's gotten to the point where there are at least some like space telescope things that they keep them aligned by the radiation pressure is pushing them one way and they have another thing to correct against that. And this helps keep things from getting overloaded and such. Because several of the things that should have kept working have broken over time. Because a lot of these things are well past their design end of life date. And shorter wavelengths correspond to more energetic photons. So if you shine light on a metal, it has to be a short enough wavelength to knock free electrons. And if it's longer than that, it never will. And the electrons it knocks off, well, if you shine one constant wavelength at a metal, it will only knock off electrons at one speed. So that's the photoelectric effect. That's one of the things where light acted like a particle. So what we can learn from light. So by analyzing the light we see, we can get a lot of information. Because light interacts with stuff. It's electromagnetic waves. The electromagnetic force is one of the fundamental forces of the universe. Lots of things will interact with light. And so one of the ways we can study light is we can do spectroscopy. Spectroscopy is the study of the properties of light that depend on wavelength. So you take light you get from somewhere, you spread it apart into its individual wavelengths, and you compare the various wavelengths to get some idea of what's going on with this light. So when you spread that light out through a prism, for example, it's called a spectrum. So a rainbow is a spectrum, and the device that makes a spectrum is called a spectrograph, or a spectrophotometer, or the spectrometer, or something like that. So there are three main types of spectrum. Anything with a temperature will emit a continuous spectrum. Anything that has a temperature has stuff in it that is jiggling. That stuff has an electric charge, presumably. Jiggling electric charges generate light. And it turns out that anything with the temperature, any sort of dense object that is hot, produces a spectrum that we can see. So if you've seen like an incandescent light bulb, it's got a wire in it that gets hot, that lights up the room, white, generating white light. The sun is a big dense ball of hot plasma. it's hot. That generates the light that is coming to us. And this produces a continuous spectrum. It generates all wavelengths with a peak of where it is most energetic and brightest that depends on the temperature. So it's an uninterrupted band of color, and how bright it is and where the strongest wavelength in that distribution is depends on the temperature. So you can see this if you take something and you heat it up. Again, like a light bulb turning on or just something heating up. It'll start dark, where it's primarily emitting infrared light. Then eventually it'll turn red. Then it can turn like an orange, slightly more orangish, and it'll eventually turn white. So you may have heard the term white hot. That's a particularly high temperature that is generating all of visible light in significant amounts. And it turns out as you go up, it'll get bluer, but there is actually sort of a practical limit because it will always be generating all the wavelengths. So you can actually work out the color of infinite temperature that you would see as a human. It's sort of a nice sky blue. It's sort of but generally very hot things are white or white blue. So very, very hot things are more bluish because they generate more blue light than red light. But also there's another type of spectrum that you get from things that are generating just specific wavelengths. This can be, you have something jumping between, you have electrons dropping down between energy levels in an atom, or you could have electrons jumping down between energy levels in some more complicated structure, like something in silicon, like this. This light is being generated in that manner. It's just one frequency, red. And that's because there's some silicon structure in here that is set up so that it only has a transition that generates that wavelength. And this, if you excite an atom, you'll get a series of bright lines of particular wavelengths that depend on the gas that produced them. So this is generally, when we see it in space, it's some low density gas being excited by something else. So if you have like a nebula that's being heated up by bright nearby stars, but you're seeing the low density gas from a different direction, and it'll glow red because it's being excited and it's dropping down. If you want to see this in a regular day-to-day experience, neon lights. I'll use this. To get different colors, they use different gases. If you've ever seen those like awful yellow streetlights that wipe out all color, those are using sodium. And sodium has two very, very strong lines right next to each other in the yellow. And it just, if that's the only color, it makes everything seem like it's black and white almost. And those lights, they put out a lot of light for very little electricity. So they're efficient, but they do wipe out all color. But yeah, that's one. And then the other thing you can have is you can have a continuous spectrum going through some less dense material. And that material will absorb some of the light. And that is the same transitions that cause the bright line emission spectrum just going in the opposite direction. Emission spectrums are when electrons fall down between energy levels in an atom. Absorption spectrums come when electrons get knocked up between energy levels. And they'll only absorb the energy that will allow them to jump between the two energy levels exactly. So you get dark lines. And this type of absorption spectrum is the most common type of spectroscopy that gets used because it lets you identify whatever light is sort of passing through. If you want to study something on Earth, you can shine specific light through it to study its absorption spectrum to get information about it. It's a continuous spectrum with dark lines running through. So the three types of spectra: a hot light source will generate a continuous spectrum, like the sun. A not very dense gas source that's excited, that's hot, will generate an emission line spectrum, like a neon tube. They don't excite it. Neon tubes are excited using a different method than just heat. They're excited electrically, but it's the same principle. And then lastly, when light passes through a cool gas cloud, certain lines will get absorbed. And that can tell you about what the light has passed through. So that's very helpful, because anything that you can see light passing through it, you can get some information about what it's made of. So continuous spectra tell you temperature, and you can also figure out sort of size by working out, comparing the continuous spectrum and the brightness, if you know the temperature and the brightness. But the continuous spectrum primarily tells you temperature. Emission and absorption spectra tell you what stuff is made of. You can get a bunch of other information as well, because you can also use it to figure out things like whether that thing is moving through the Doppler effect and other properties. So here is a short video about the three types of spectra.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to distinguish between the three types of spectra that are useful to astronomers. What's a spectrum? Spectrum is the singular and spectra is plural. Spectroscopy is the study of the properties of light that are wavelength dependent. So that's what's illustrated here on this diagram. You will see that squiggly line in the middle. That squiggly line is showing the wavelength of different forms of light. Now, you're probably most familiar with the visible portion of the electromagnetic spectrum. You know that the color of light can range between red, orange, yellow, green, blue, violet. Those different colors are different colors because they are different wavelengths of light, with red having the longest wavelength of around 700 billionths of a meter, 700 nanometers, and blue having the shortest wavelength, around 400 nanometers. The shorter the wavelength, the more energetic the light is. So blue is more energetic and red is less energetic light. If we pass light through a prism, we see that it will spread out. As white light passes through a prism, the color with the shortest wavelength, violet, is bent more than blue, which is bent more than green, which is bent more than yellow, which is bent more than red. And so basically the different colors of light, the different wavelengths of light, separate out into a continuous spectrum. That's what's shown up here at the top. So that's a good starting point. However, in terms of astronomy, what is more useful is either the dark line spectrum or the bright line spectrum. Consider the dark line spectrum first. This is where you have a source of light that then passes through some quantity of matter, some cool gas. In other words, when I say cool, I'm saying that it's not hot enough that it's giving off its own light. And instead, the matter that is in that cool gas absorbs some of that light. And as a result of absorbing it, the light that makes it out of the other side of that gas cloud is missing some portions of the spectrum, the portions that were absorbed by whatever gases are in that cloud. This results in the dark line spectrum. Another good name for the dark line spectrum is the absorption spectrum. So the black lines there are what's missing because it was absorbed. Notice that that pattern of black lines is distinctive, and each type of matter, each element, absorbs a different combination of wavelengths of light. So it's almost like a fingerprint or one of those barcodes that you see on products that you buy at the store. Each pattern of lines is indicative of a particular kind of matter. Now let's look down at the bottom. Here we don't have some external source of light, but instead we have some hot gas. So this is gas that is hot enough to be emitting its own light, and as a result of that, it's emitting it in terms of the matter that is present there. And so you'll see that you end up getting a bright line spectrum instead, where most of the light is not there because there's nothing to generate it, no external source of light. and only the matter that's there is giving off light in the particular wavelengths that are distinctive to that matter. You will notice that the bright line spectrum on the bottom matches the pattern of the dark line spectrum above, except it's reversed in terms of what's light and what's dark. Here are two example bright line spectra. These are for the elements hydrogen and helium, which are the most abundant elements in the universe. You will notice that both of them have a prominent red line over on the left, and that red often shows through in terms of what we can visually see when we look at incandescent gas clouds giving off light. An example of that is the nebula in the constellation Orion, which is shown here. You'll see it has a very distinct reddish color. That's basically because it is dominantly composed of lots of excited hydrogen gas. Thanks a lot for your attention. This has been another Smart Figure.
Spectroscopy is a study beyond astronomy. It gets used in all kinds of stuff. Actually, in geology, it gets used for identifying materials. There are these handheld X-ray spectrometer devices that use X-rays to check the absorption of the elements like in a rock or in some material. You can identify what elements are there, things like that. So here's a comparison. This is the emission line spectrum for hydrogen from blue to red, and this is the absorption line spectrum for hydrogen. You'll notice it's the same lines, because these transitions are, each of these lines corresponds to a transition between two energy levels within the atom. And you can, this is basically, the emission line is when you go down, the electron falls down, and the absorption line is when an electron gets pushed up. But the amount of energy to go between two levels is always the same. Now, sometimes you can have some differences where, because of like the resting state of atoms, some of the absorption lines might be more prominent than others, or some of the emission lines might be more prominent than others. Like there are certain lines that you're unlikely to see, but generally they're the same. It's the same sort of fingerprint. Because sometimes like the transition might be between like level 3 and level 4. And if atoms aren't normally in level 3, that absorption transition isn't going to show up very often. So most stars have an absorption line spectrum. If you take the spectra of a star, you'll see a bunch of these absorption lines. And this can be used to tell the composition of it. It can also be used to figure out other information about it. It turns out by studying the absorption lines, it's another way you can figure out the temperature. If that light is, say, passed through a cloud of dust or something that has made it so it's harder to use the blackbody radiation to figure out the temperature, you can use the absorption lines to figure out the temperature. Because different temperatures ionize different stuff, and different amounts of ionization change which lines are strong. So we'll get into that later, a little bit later. So every object radiates a continuous thermal spectrum that depends on its temperature. And that's every object. That's not just like stars, but also you and me. Now, I am emitting a continuous thermal spectrum that is peaking in the infrared. And so if you measure the total energy output, the intensity, well, hotter objects, it turns out, radiate a larger portion of their energy at shorter wavelengths than cooler objects. So by basically studying the curve and figuring out where the peak would be, you can determine the temperature. And this is how we can figure out the temperatures of stars. That's one of the ways we can figure out the temperatures of stars. But it is also how an infrared thermometer works. An infrared thermometer figures out where the peak of the output would be, and calculates the temperature based on that. And also the amount of energy pumped out per square meter depends on the temperature. So if you know the temperature and the brightness, how much energy how much light the thing is putting out, you can figure out how big it is. So you can actually use this to help figure out the size of objects. So here are some examples showing the relative intensity of light from different surface temperatures. So Earth peaks at around, Earth has a temperature of 287 K. So it peaks at around 10 to the 4 nanometer wavelength. In the infrared, Betelgeuse is about 3000 Kelvin. So it peaks at around 1000 nanometers. And so it appears primarily a red star. The sun is around 6000 Kelvin. So its peak is right in the middle of the visible light spectrum, around 300 or 400 nanometers. And so it's a yellow star, and you get sort of whitish light from it. And then here, Rigel, which is at 12,000 Kelvin, peaks at around 100 nanometers in the ultraviolet. So this appears to be a blue-white star because it's got sort of an even distribution of all the colors, but it's got more blue than red, which makes it look bluish. But you can see how, as these peaks continue to move over, they'll still always give you all the colors. So it turns out really, really hot stuff looks bluish white. And it's possible to theoretically calculate the color of infinite temperature, which is kind of amusing. Now, another thing we can look at, so there's these fingerprints for various elements. And we know where they should be. If an object is moving towards you or away from you, the waves get, if an object is moving away from you and emitting waves, the waves get stretched out. Because as it emits waves, it gets further and further away from you. So effectively, the wavelength is increased. If it's coming towards you as it's emitting waves, it's following up the waves, so the waves get compressed. And this changes the wavelength and the frequency of those waves. So this is a change in wavelength and radiation caused by the relative motion of the source and the observer. So if you're moving towards something, waves get compressed and shorter. And that is what is called by astronomers a blue shift, because they're shifted towards shorter wavelengths. They're shifted towards the blue. If they are going away from you, they get stretched out and get longer. And this is called a red shift with light. Because it is getting longer, it's shifted towards the red, so it is a red shift. And the amount it gets shifted depends on the velocity. The same effect can happen with any sort of wave, so like sound waves have the same effect. You can hear this with when something is driving past you, it sounds higher pitched as it's coming towards you and lower pitched as it's going away. The most extreme example of this is if something is traveling faster than the speed of the thing it emits, all the waves end up piling onto each other and you get a sonic boom. That happens with sound. It does happen with light because nothing goes faster than light. And the size of this shift, the size of this wavelength change indicates the velocity. So higher velocities have a larger Doppler shift. And if you've seen something called Doppler radar, they're using the Doppler effect to study the movement of raindrops in clouds for weather. And also, this is how radar guns work to check your speed. They bounce radio waves off of you and look at the change in wavelength. So here's the Doppler effect for a moving sound source. As the sound source moves, you get higher pitched sound when it's moving towards you, and lower pitched sound when it's moving away. And it's just because it's moving, it sort of piles up the waves in front of it, and the waves behind it stretch out. So here's a short video about the nature of the Doppler effect.
Hi there, students. This is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe what the Doppler effect is and how it's useful to astronomers. Let's start off with this. This is a refresher of what a bright line spectrum looks like. This is the bright line spectrum for hydrogen. It is distinctive not only in terms of the number of bars that is displayed and the spacing between those bars, but also in terms of the specific wavelengths that we see. Now let's imagine that we aimed our spectrometer at some distant star and we saw this instead. At first glance, it looks pretty similar, but if you look closely, you'll see that all the lines have been offset a little bit towards the left. In other words, a little bit towards a longer wavelength, towards the red side of the spectrum. This is an example of the Doppler shift. You are probably already familiar with the Doppler shift because it's something that we encounter regularly when some source of noise approaches us or moves away from us. So think about an ambulance that's approaching you. As that siren on the ambulance is wailing away, it's generating sound waves, and those sound waves reach your ear. If the ambulance is moving towards you, then the wavelength of those sound waves gets compressed as the source gets closer and closer to your ear. Similarly, as the ambulance moves away from you, you see that the wavelengths get stretched out. And so the sound will be different as the ambulance approaches versus moves away. The same thing is true for light, which also has a wave-like character. So if we look at visible light and we see it is shifted towards the red side or the longer wavelength side of the visible spectrum, that implies that the source of that light is moving away from us. And if it's shifted towards the blue side of the spectrum, the opposite is true. The source of the light is moving toward us. Here's an example. This is the spectrum for the element sodium, say in some planetary atmosphere. But if we look at that planetary atmosphere and we see that the sodium spectrum is shifted towards the red side of the spectrum, that implies that that planet must be moving away from us. If it's really moving away from us at a fast rate, then we would expect to see a larger shift in the spectrum of those same sodium lines. All right, now what would this mean? That's an example where the sodium lines have been shifted towards the blue side of the spectrum. And so therefore, that planet would be moving toward us while it is emitting that light. Okay, good job. Thanks a lot for your attention. This has been another Smart Figure.
And one of the most dramatic things with the Doppler effect was quasars. When they studied the spectrum of quasars, they didn't know what they were. They were really weird looking things until they eventually realized they were actually seeing the spectrum of hydrogen massively redshifted. And they realized that these things were moving away from us incredibly fast, which actually implied that they were incredibly far away from us. Because the biggest source of redshift, stuff moving away from us, is the fact that the universe is expanding. So if you go far enough away from us, everything is moving away from us. And the further away from us, the faster it's moving away from us. So to observe things, we need, to see all this electromagnetic radiation, we need to collect it somehow. We need to collect light so we can observe it. And to do that, we use telescopes. We're going to start with the original type of telescope, the optical telescope, that collects visible light. So first telescopes were invented in the Netherlands. We used a couple of lenses to collect visible types. So there's two basic types of telescope. There is a refracting telescope. These use a lens called the objective to bend or refract the light to produce the image. The light converges in an area called the focus, and then there's a second lens called the eyepiece that is used to examine the image directly. One of the problems with refracting telescopes is something called chromatic aberration. This is a problem with all lenses. they distort color. Because basically, lenses act like prisms. They bend light. But they act like prisms, which means they bend different wavelengths, different amounts. And that spreads and distorts images and spreads out colors. And it can be a real issue. So there are ways to correct for this. Camera companies spend an enormous amount of money to do this, which is part of why camera lenses are so complicated and expensive. But this is one of the issues with refracting telescopes. Also, really big lenses are really awkward because you can only hold them at the edges and they need two surfaces to be optically perfect. So this is a refracting telescope. You have an objective lens and you have an eyepiece. Now these were the first telescopes developed. They work, but in general, for serious scientific purposes, nobody uses refracting telescopes anymore. The other type is a reflecting telescope. The first reflecting telescope that's well known was put together by Newton. It uses a concave mirror to gather the light. So instead of bending the light with a curved lens, it reflects the light so that it gathers at a point with a curved mirror. Using a mirror, there's no color distortion. All colors bounce off mirrors the same. And nearly all large telescopes are of this type. It's just much more straightforward to build a really big mirror than to build a really big lens. And you can support the mirror from the back, and only one side needs to be perfect or optically up to optical standards. So this is a reflecting telescope. So this is a reflecting telescope of the style called a Newtonian focus, where light comes in, bounces off the mirror at the back, hits a secondary flat mirror, and comes out the side through an eyepiece. So Newton's first telescope was of this type. Lots of the telescopes that you might buy as a hobbyist, that you would use as a person, are of this style. There's several different ways you can set up where the light comes out of your telescope. For serious research telescopes, something called the Cassegrain focus is used, where instead of bouncing out the side like this, there's a mirror here and it bounces out a hole in the back. So then you can put your detectors behind your mirror. That's pretty common. And then there's some other styles. Here, for example, is the mirror for a large telescope. I think that's the one from the Hubble. And that's a Cassegrain focus. So this plate in the center will be removed, and there's the hole there. So here's a short video about the types of optical telescopes.
Hello students, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at optical telescopes. After watching the video, you should be able to distinguish the two types of optical telescopes and state the advantages of reflecting telescopes over refracting ones. Much astronomy nowadays is done with radio telescopes that do not collect visible light, but instead are collecting things such as radio waves. But astronomy didn't start there. Astronomy instead started with optical telescopes looking up at the sky with the eye. The eye alone is not all that effective an instrument, so telescopes basically allow us to catch more light. A refracting telescope takes incoming light, focuses it to a single point, and then spreads it out again over an eyepiece. This is the most basic sort of telescope. However, they don't get too much larger than this because that large lens has some problems. One problem with the lens is if it gets too big, then it tends to distort and warp under its own weight. And a more important issue is the fact that the lens, being a thickness of glass, basically acts like a prism, and so it starts spreading out the light. The bigger the lens, the more this is an issue. So, most modern telescopes that we use are not refracting telescopes, but are instead reflecting telescopes. The way these work is incoming light hits a parabolic mirror, a curved mirror on the back of the telescope, which then refocuses the light on a smaller mirror and that sends it up to the little lens where the person is looking in. This approach was first developed by Isaac Newton, and this is his reflecting telescope that he designed. Reflecting telescopes have gotten a lot bigger since then. For instance, this is a look at the 2.5 meter wide parabolic mirror on the inside of the Hubble Space Telescope. Because this is a mirror rather than a lens, it doesn't suffer from those effects of internal warping due to high mass or that chromatic aberration which is caused by the prism-like spreading out of the different wavelengths of light. As a result, our images of space have gotten much better, and we can now distinguish objects that we weren't able to distinguish prior to the development of the reflecting telescope. Thanks a lot for your attention. This has been another Smart Figure.
So to just keep making them bigger and bigger. So we're starting to approach the practical limit with the extremely large telescope that they're currently building at the European Observatory. The European Extremely Large Telescope, that's the name. They're building in the European Observatory. So another thing we've moved on from is using your eyeball to detect and record light. So the problem with that is that your eyeball is connected to your brain, and your brain is basically, it evolved to keep everything working, keep you from dying kind of thing. It didn't evolve to accurately record images. And also you don't want to sit there and watch for ages. So we've moved on from that to other technologies that are mechanically or electrochemically or whatever, recording the light that comes in. So the original thing that was used was photographic films, photographic plates, generally glass plates coated in light-sensitive chemicals. These are not distorted by human bias, and they can expose for hours. You can expose them for a very long time to collect lots of photons, so you can see much fainter things than you can see with your eye. Because your eye, the detecting things in your eye are very sensitive, but they refresh all the time. So you're limited. You can't like expose for hours. The photographic plates have been mostly primarily replaced by charge coupled devices. These are digital detectors. It's the same technology that's used in like your cell phone. The camera in your cell phone probably uses a charge coupled device. And what it is there's specially dubbed silicon that when a photon hits, it knocks an electron up into a little area that's sort of stored. And so they can also be exposed for an extended period of time. They collect a lot more photons than photographic film does. So photographic film interacts with about 1% or a few percent of the light that hits it. Charge coupled devices are like 60 to 70%. So almost all the photons that hit the chip. You can greatly increase your exposure time by just having it exposed on the chip for a long period of time. The photons build up, and it can be very quickly and efficiently read off because it builds up electrons, and then you can just read them off digitally. And so you don't have to develop your photographic plate and look at it. You immediately get something into a computer that you can use right away. Some also other things that have been developed over time: active optics. So motors that drive the telescope, they can sometimes rearrange the positioning of the mirror, but also sometimes even change the shape of the mirror to correct for distortions caused by the atmosphere. Yeah. Oh, that's more adaptive optics. Active optics is that you direct the pointing of the telescope to compensate for certain distortions, while adaptive optics, you can cancel out atmospheric turbulence. They sort of combine. And arrays of telescopes that work together can do some very interesting things. So this is how the Very Large Telescope from the European Observatory, by using a very specialized setup to do what's called interferometry with optical light, they managed to take an image of an exoplanet, a planet around another star. So here we can see comparing the resolution of two telescopes. This is a telescope with less resolution. This is much higher. And the main way you increase the resolution of a telescope is you make its mirror bigger. Turns out the limit of resolution depends on the size of the mirror and the wavelength. The ratio of the size of the mirror to the wavelength determines the limit of resolution. And there are tricks to get even higher resolution by combining information from multiple telescopes. That's what interferometry does. But it's very difficult with light. You need very specialized, delicate optical setups to pull it off with light. It's done much more commonly with radio waves. So one of the things that we've done more recently is the development of radio and space-based telescopes. This is all fairly recent because radio technology is maybe 100 years old. And the first radio telescope stuff happened in maybe the 30s, so maybe, yeah, about 100 years ago. And space, we didn't put stuff wasn't put into space until the 50s. So radio telescopes. So I mentioned that the resolution of a telescope is related to the size of the telescope and the wavelength, and it's related to the ratio of them. What that means is the bigger your telescope, the better your resolution, but the bigger the wavelength, the worse your resolution. So to compensate for that, you need to make a bigger telescope. Radio telescopes are much physically larger than optical telescopes because radio waves are about 100,000 times longer than visible light in wavelength. But one of the advantages, you don't need to make the surface as perfectly smooth and nice like you do with optical telescopes, because the waves are 100,000 times longer. So optical telescopes need to be very carefully and perfectly ground to be perfectly smooth to the right shape. They can't have any distortions on the surface because visible light is a few hundred nanometers in wavelength. Radio waves are centimeters long. They're, this size. So radio telescopes, the reflecting mirror is usually made of wire mesh. So you can see through it. Because of the fact that there's that, the much longer wavelength, they tend to have a rather poor resolution. But we can combine them together into a network called a radio interferometer to act as if they were a larger telescope. So it turns out if you have multiple telescopes and combine them together, you can make them act as if they were a telescope that was the size, for resolution purposes, the size of the distance between the telescopes. So if you have an array of radio dishes spread out over a square kilometer, you effectively have a square kilometer sized telescope. If you combine your information, there's a square kilometer array being built right now. Now, this is the biggest steerable radio telescope in the world. Just for scale, this is freaking enormous. For scale, I think that's a van. That tiny thing down there. This up here, that's a story. You could go up there and stand in that room. There's a room up there. That's like a story tall. So this is the primary reflector. Here's the secondary reflector and the receiver. But this thing is enormous. It's 100 meters across. It is in Green Bank, West Virginia. And the reason it's in Green Bank, West Virginia is that area is where the US military tests its radio equipment. So the whole area is a radio dead zone. There aren't any radio transmissions allowed in the vicinity. So everything has to be specially shielded. You aren't allowed to have a cell phone, anything like that. Oops. So this is the biggest steerable radio telescope in the world. It's not the biggest radio telescope in the world, because if you want to build it bigger, you don't move the dish. But this is the 100-meter steerable round beam telescope. So, and it is possible to actually do crazy things with radio interferometry. The most impressive I know of being the Event Horizon project, which used radio telescopes over the entire Earth to effectively create a radio telescope the size of the Earth that was able to take images of 2 black holes. The black hole in the center, the supermassive black hole in the center of the galaxy M83, and then the supermassive black hole in the center of our galaxy. So, some advantages of radio telescopes. They're basically unaffected by weather, much less at least. The radio waves that we are looking at will just go through clouds. They don't care about them. They also work during the day. Because, during the day you can't use an optical telescope because it's washed out by the sun. But the sun doesn't pump out that much in the way of radio waves. So radio telescopes work just fine during the day. They're relatively less expensive. It's a lot cheaper to make a big dish out of wire mesh than it is to make an optically perfect mirror, tens of meters across. They can be used 24 hours a day. Also, there's a great big advantage to be looking at a different wavelength. If you are looking at a different wavelength, you see different things. You detect different materials. So one of the things radio telescopes can do is they can observe cold gas. So cold hydrogen gas, which is all over the place throughout the universe, turns out emits radio waves. So we can detect those radio waves and study them. And they can see through interstellar dust clouds. So for people who are trying to study the births of stars, stars are born in clouds of gas and dust. If you want to study the birth of a star, you need to use wavelengths that will penetrate those clouds of gas and dust. So radio telescopes work for that. They also use infrared, but you can't do infrared from the surface of the Earth very easily. And the other thing, if you look at the atmosphere absorbs most of the light that's coming from space. Most wavelengths get absorbed by the atmosphere. There are 2 windows where light will pass through. There's the optical window, which is visible light and a bit of ultraviolet and a bit of infrared on either side. And there is the radio window, which is used by radio telescopes. But if you want to look at most infrared light, if you want to look at ultraviolet, X-rays, gamma rays, any of those, you have got to go above the atmosphere. So we put our observatories in orbits. And even if you're looking at visible light, there are advantages to going above the atmosphere, because one of the biggest problems is the distortions caused by the atmosphere. Because what you're looking at, you're looking through this turbulent fluid that is distorting things. So you can detect light without the interference of the Earth's atmosphere. So the Hubble Space Telescope is an optical reflecting telescope. It's orbiting the Earth. It collected evidence to support the nebular hypothesis of solar system formation. It's allowed us to look further out and further back in time than, anything before the James Webb Space Telescope, which can look even further than the Hubble. And it's just been an amazing thing, and it's kind of shocking when you find out how many times something has broken on it since they've lost the ability to actually go up there and fix it anymore. that it's still working. And there are more than 100 space observatories that have been launched, and they can detect visible, radio wave, infrared, ultraviolet, X-rays, and even gamma rays. So space-based observatories are used for all kinds of stuff. Probably the most impressive current space-based observatory is the James Webb Space Telescope that was launched relatively recently. It's primarily an infrared telescope that goes up into the visible, but like not all of the visible, just like the red portion. Because they're actually interested in stuff that is very far away and thus very redshifted. So they designed the telescope to primarily be infrared and the red end of visible. So here is the diagram showing the approximate depths to which various wavelengths of light penetrate the Earth's atmosphere. So you can see gamma rays, X-rays, and ultraviolet light just don't make it through. Some infrared gets kind of low, so you'll notice that it gets down to the level of where planes fly. There's actually though they recently, like as of just this last year, stopped flying it. NASA had a 747 with an infrared telescope in the back of it, and had a door that opened up, point the telescope up. And sometimes they'll send infrared telescopes up on weather balloons to observe. And then there's a bunch of space observatories. So these are things like, the Swift Gamma Ray Observatory, the Chandra X-ray Observatory, Hubble Space Telescope, the Spitzer Infrared Observatory, which kind of been replaced by the James Webb Space Telescope, the Planck Observatory, and the Spectra R. And then there's the radio window stuff that makes it through. So those are the types of telescopes and the various ways we can observe the universe. Any questions about that? Yeah, so we're starting to reach the biggest size you can practically build a telescope on Earth. It's almost 40-meter across European extremely large observatory is currently under construction. It should finish in a few years. But yeah. So let's talk about our star, the sun. The sun is one of the 200 billion odd stars that make up the Milky Way galaxy. We look out, there are a lot of stars. It is the only star that is close enough to allow the surface features to be studied in any detail. We've managed to sort of image the surfaces of a couple other stars, but it's like there is a fuzzy dark spot on this star. It's not any detail of the surface, because I think we observed a darkening of Betelgeuse, where Betelgeuse had a dark spot. And the sun is nothing special. It's a pretty average star. It's pretty middle of the road. So let's talk about the structure of the sun. What we see in the sky, the thing we see that emits light, is what's called the photosphere. It is the sphere of light. Photo, light, sphere, sphere. That's the sun's surface. It's actually just the point where, as you're looking into the sun, it becomes opaque. It's a layer of incandescent gas that's maybe less than 500 kilometers thick that you're seeing. And if we observe the surface in detail, it's sort of grainy. It's made of many small, bright markings called granules with darker areas around them. And these are produced by convection. What's going on is in the center of these bright areas is where material is hot spots where material is welling up. And the darker areas are where material is sinking down, and they're cooler. This is the same process that you can create this sort of grainy cellular pattern on the surface of like cup of tea or something with milk in it, those patterns. That's convection. And pretty much all the elements that are found on Earth occur in the sun. We've observed basically every element that occurs on Earth. I mean, there's probably some exceptions there, but they're like things we create artificially or, yeah. But basically everything we find on Earth, we find in the sun. And the temperature of the photosphere, the surface, is around 6,000 Kelvin, which is around 10,000 degrees Fahrenheit. And so it glows white hot and generates the light we see. So the surface, so the structure of the sun, there's several layers. The center of the sun, there is the core. This is the hottest, densest portion of the sun. This is where nuclear fusion occurs and is what actually powers the sun and generates the energy that the sun emits. Above that is a layer called the radiation zone. In the radiation zone, energy is transmitted primarily by radiation. It's not, energy is moving around because stuff is emitting radiation, absorbing radiation, emitting radiation again, and it travels outward via radiation, but not by, say, the movement of material. Above the radiation zone is the area called the convection zone. In the convection zone, energy is primarily carried by hot gas or hot plasma rising up to the surface and cooler plasma sinking down. So it's carried by convection instead of via radiation. So, energy being carried by radiation, that's like in a toaster oven or a traditional oven, is mostly radiation, sort of. And then energy carried by convection, if you have an air fryer, that's what an air fryer does. It moves the air around to carry things by convection. And then the surface of the sun that we see is called the photosphere. Above that, in the atmosphere of the sun, is a layer called the chromosphere, which glows red because the gas in it is excited by the photosphere below it, by the magnetic field of the sun and other things. And then above that is a layer called the corona, which extends out much further. It's much thinner. And the way that the chromosphere and the corona were first discovered was during solar eclipse. You can have the photosphere blocked out, but you can still see the stuff around the edges, basically. And we can have various surface processes. So the surface of the sun is sort of granulated. It's got these convection cells. There are dark spots that are cooler called sunspots. These are tied to where the magnetic field punches out of the surface and punches back in. We get also things like prominences, which are these big arcs of material being drawn up along the magnetic field lines. So here's a short video going over some of the structures of the sun.
Hello students, welcome back for another Smart Figure. This is Callan Bentley, and this time we're going to take a look at the structure of the sun. By the time we're done watching this video, you should be able to describe the 4 major regions of the sun and describe some of the key characteristics of each. The sun is important not only because it is the energy source for just about all life on Earth, but also because it is our nearest star. And so if we want to understand what's happening with most of the mass in the universe, we need to be looking at stars, but there's only one that's in the immediate neighborhood and therefore available for close observation. Because the sun is bright and it would blind us if we looked directly at it, we have special solar observatories such as this one in Arizona, which essentially take light from the sun and project it onto a wall where it can be observed safely. By studying the sun, we've come up with a model for its internal structure. And you can see here that we have the bulk of the sun, which we cannot see, which is its interior. And then above the solar interior is the part that we can see, which is called the photosphere. And then there are two parts to the sun's atmosphere, the chromosphere and the corona. I don't have too much to say about the solar interior, except that it probably has a core on the basis of its overall mass. And of course, that is where fusion is taking place between lightweight atoms to make heavier weight atoms. The result of that fusion is that energy is released, and of course, that energy is what powers life on Earth. Let's now take a look at the photosphere. If we look at it, we see that it is granular in nature. There are these light-colored areas, such as we see right here and here and here. And then in between those are darker colored areas. These are ephemeral features. Each one lasts about 10 or 20 minutes, and they're called granules. And the granules are thought to represent upwellings of material from the sun's interior to the top of the photosphere. And then where it gets dark again is where we think it's cooling off, losing heat, and then sinking back down to be rewarmed again. Of course, that process is called convection. When we look at the spectra of the sinking dark regions between the granules, we see that most of the sun is made out of hydrogen and helium. About 90% hydrogen and a lesser amount, about 10% of helium, with all the other elements, and in fact it does look like just about every other element we know about is there, but in much, much smaller amounts. The sun's atmosphere consists of the chromosphere and the corona. The chromosphere is the part that is shown here in this pinkish sort of color here on this diagram. You can see that there are little filaments that stick up. These are called spicules. Here's a look at some of the spicules sort of on the edge of the sun as viewed at a solar observatory. The chromosphere is several thousand kilometers thick and is dominated by hydrogen as indicated by its reddish color, which is the bright line spectrum that we see emanating from this part of the sun. Hydrogen, of course, has a very prominent red band in its spectrum. This is actually the place, ironically enough, where we first discovered helium. It was discovered in the sun's chromosphere on the basis of its spectrum, and it's because we discovered it there that it's named helium. That comes from the Greek helios, for sun. It was only much, much later that we discovered it on Earth coming out of a natural gas well. Finally, there is the corona. The corona is an envelope of ionized gases that extends way far out away from the sun, and we would never see the corona except during times of solar eclipses or with special equipment that blots out the incredible light that comes from the photosphere. You can see here that the corona has a wispy, sort of filamentous structure to it. Some of the material in the corona is moving at really high speeds, speeds that are great enough that it allows these highly charged particles to actually escape the sun's gravity and go moving out into space. There we know them as the solar wind. The solar wind travels outward from the sun at between 250 and 800 kilometers per second. This is the phenomenon that's responsible for the tails on comets, where the solar wind particles are banging into the comets, vaporizing some of that material, and then dragging it off in a down-sun direction. In other words, away from the sun. It is also the source of the energy that causes the northern lights when it interacts with Earth's magnetic field and Earth's atmosphere. Thanks a lot for your attention. This has been another Smart Figure.
So the chromosphere is just above the photosphere. It's the lowermost portion of the sun's atmosphere. It's a relatively thin, hot layer of incandescent gases. It's a few thousand kilometers thick. And the top has these numerous spicules, these very thin, narrow jets of rising material. And above the chromosphere is the corona. This is the outermost portion of the sun's atmosphere. It's very thin and tenuous. And this is where the ionized gases that escape from the corona through what are called coronal holes, they escape and produce the solar wind. And the solar wind is this stream of particles, charged particles being flung off from the sun that flies outwards continuously, causes things like auroras. So the northern lights are caused by those particles being redirected by Earth's magnetic field and hitting the atmosphere and exciting the atmosphere. The temperature at the top of the corona actually exceeds 100 million Kelvin, because the corona and the chromosphere are both heated by the magnetic field of the sun, so they get very hot. And the solar wind and the sun's magnetic field make a bubble that's called the heliosphere that sort of defines the edge of the area dominated by the sun, and it extends well beyond the orbit of Pluto. It's maybe somewhere on the scale of around 100 astronomical units out, while Pluto's at like 40. It's like twice the distance from Pluto that Pluto's at. And here's the corona, as seen during an eclipse. The corona is called a corona because it looks vaguely crown-like. That is what corona means, which means lots of things that are spiky get called corona. There was a significant spiky thing that happened recently that got called corona. That is where it comes from, crown. Now, the solar interior, we can't look at the solar interior directly. The photosphere is in the way. But the surface vibrates. And so we can actually study how the surface of the sun vibrates to get some idea of the internal structure. So there are sound waves that are passing through the interior of the sun. We do something very similar on Earth to study the interior of the Earth. We look at waves passing through the interior of the Earth, earthquakes. So the core is the region where the sun's energy is radiated. That's where fusion actually occurs. It's only about 25% of the diameter. Of the radius. Yeah, it's only about 25% of the radius in size of the whole sun. So it's quite a bit smaller. So when the sun runs out of fuel, there'll be plenty of hydrogen left. It'll just be outside of the region where it can fuse. The radiation zone above the core is a dense zone where radiation is constantly absorbed and re-emitted. So energy is transmitted primarily by radiation. And then between the radiation zone and the photosphere is the convection zone, where energy is transmitted by convection. And in the core, in the center of the core, is where nuclear fusion occurs, and this is the source of the sun's energy. This is done via what's known as the proton-proton chain, by which 4 hydrogen nuclei, protons, combine to form 1 helium nucleus. So 4 hydrogen nuclei are converted into a helium nuclei, and in the process, some of the mass of those nuclei is converted into energy. 600 million tons of hydrogen gets consumed each second, and the sun has enough fuel to last another 5 billion years or so. So deep in the sun's interior, there is this process called the proton-proton chain, where 4 protons combine to become 1 helium nucleus. They don't do it in one step. First, 2 of them combine in pairs, then those combine with another proton, and then the things that are made from those combine to form a helium nucleus. So there's a chain of steps. And I think that's where I'm going to stop for today. An interesting factoid that unfortunately you will not be able to observe. There is going to be a lunar eclipse this weekend. Unfortunately, it's only visible in like Europe, Asia, and Africa. We're on the wrong side of the world to see it. But there is going to be a lunar eclipse this weekend. If you do want to try and see an eclipse, Wikipedia has a list of all the upcoming eclipses for the next couple hundred years. They're very predictable. Yeah, so have a nice day, and I will see you guys next week.